Hi there, my name is Sarah Wilson and welcome to my video on solving a truss. Solving a truss has three main parts. First, we're going to decide, is the truss statically determinate? Second, we'll find the external reaction forces. And third, we'll find the internal forces. Let's start with deciding if this truss is statically determinate or not. In this diagram up here, I've got a truss that's supported on one end with a pin and one end with a roller. And I've got some distances on the members themselves, and I've labeled them A, B, C, and D at the joints. And I've got 100 pounds of force on the top. That's the only applied force in this problem. Let's go ahead and start by removing the pin and the roller and replacing them with their forces that they represent. A pin has both horizontal and vertical forces. So this is FAX. Oh, I'm sorry, this is FAY. And then I've also got FAX in the horizontal direction. And then the roller only has one force on it. And it supports it from below, and this is FDY. All right, so out of this information up here, you can decide, is this truss statically determinate? And the formula to do that is 2 times J equals M plus R. J represents the number of joints in the problem, M represents the number of members, and R represents the number of reaction forces. So J, number of joints. I've got A, B, C, and D, so that's a total of 4 joints, which gives us 8 on the left side of the equation. M is the number of members. I've got 1, 2, 3, and then this bottom section right here is actually 2 separate members. I've got AC and CD, so the 3 on the top and 2 on the bottom gives me a total of 5 members. And then the reaction forces are FAX, FAY, and FDY. There are 3 of those. 5 plus 3 does give you 8. So the formula works out. It looks like this truss is statically determinate, so we can solve it. Let's go ahead and start with the external reaction forces then. There are 3 formulas. Remember that it's the sum of the forces in the X, sum of the forces in the Y, and the sum of the moments must all total out to 0. So I'm going to begin with the sum of the forces in the X direction. They must total to 0. In the X direction of this problem, I see FAX, and that's it. So that tells me that FAX equals 0, since that's the only force in the X direction. So we have 0 pounds of force right away. Let's go ahead and do the Y direction. The sum of the forces in the Y direction must also total to 0. I see FAY and FDY, they're both pointing upwards, so we're going to call them positive in the equation. And 100 is pointing down, and so we're going to say that's negative 100. So I have FAY plus FDY minus 100. And those have to total to 0. And I have simplified this problem now. If I add 100 to both sides, it's a little bit simpler, but I have 2 variables in this equation. So that's too many unknowns to solve for. I must go on to something else and then come back to this equation later. Let's do the moments. I want to do some of the moments about A. A is our pin joint. That's the most common joint to choose for your pivot point. So I'll put a A down in the subscript. That must total up to 0 as well. All right, so in this calculation, FAX and FAY won't play a role because they go right through A. Therefore, their distance from A is 0. There won't be any terms in this equation. So the only 2 terms will be the 100 and the FDY. Let's do the 100 right now. I have 100, that's the magnitude of the force. And what's its distance away from point A? Now again, be careful. We're not talking about like diagonal distance or anything like that. We're trying to figure out the line that the force is acting in. How far away is that line from point A? So here's the line that 100 is acting in. It gets within 5 feet of point A, so we multiply 100 times 5. All right, is it positive or negative based on the rotation? Not whether 100 is pointing down or not. It's all about the rotation when you're doing moments. Put your finger at A. Imagine pushing at 100 How would this truss rotate? It would swoop around in this direction. That is clockwise. Clockwise is negative. So I would have 100 times 5, and it's a negative term. Now I have f dy. How far away from A is it? There's point A. Here's the line of f dy, the line it's acting in. That's a total of 9 units away. And is it positive or negative? Well, again, put your finger at A. Imagine pushing here at f dy. It would cause this whole truss to rotate this direction. And that's counterclockwise, so this term is positive. And those must total up to 0. All right, let's do some simplifying. I have negative 500 here, plus 9 f dy. Those total up to 0. I'll add 500 to both sides. And I get 9 f dy equals positive 500. And now we'll go ahead and divide both sides by 9. 500 divided by 9 comes out to be 55.6. And that's pounds of force. Okay. Remember that we have one other problem to go back to do here. That now that I know f dy, I can come back and substitute it into this equation and find f ay. And so if this is 55.6, you need to know what did I add to 55.6 to get it to total up to 100. So let's subtract 55.6 from 100. I get 44.4. And that's pounds of force. So right there are our 3 external reaction forces: FAX, FAY, and FDY. Now that we've got the external forces, we're ready to go on to find the internal forces. I've recorded our external forces over here, so I have more space to work. Before I start working with any particular joints, I'm going to go ahead and take a moment and find the 2 angle measures here in the corners, angle BAC and angle BDC. And those will be useful later on when we're doing our calculations at each particular joint. So I like to find them ahead of time. Let's do angle A first. So if you take a look at this little right triangle that's over in the corner, here's 3 units on the vertical, 5 units on the horizontal, and I'm looking for this angle measure right here. Now compared to this angle, this is the hypotenuse, this is the opposite, and this is the adjacent. So which trig ratio uses opposite and adjacent? That is tangent. So we're going to use the tangent of theta equals opposite over adjacent. Alright, let's write our little equation. The tangent of theta, remember theta is what we're looking for here. Opposite is 3, adjacent is 5, and now we'll do the inverse tangent of both sides. So inverse tangent on the left, inverse tangent on the right. These two cancel each other away, and now all we need is a calculator. Inverse tangent of 3 over 5. Comes out to be 30.96. So I'm actually going to go with theta equals 31.0 degrees. Alright, so that gives me this little angle right here. I'm going to mark that 31 degrees. And we'll be specific, we'll add 31.0. Okay, now let's do the same thing, but let's do it for angle B over here. Let's find this one. This triangle looks something like this. And you'll just have to pretend that's a nice looking triangle. I've got 4 feet down the bottom, 3 feet on the vertical. Yeah, definitely not to scale. I'm looking for this angle right here, theta. Again, looks like just like last time. Hypotenuse is here, opposite is here, adjacent is here. I've got opposite and adjacent is tangent again. So the tangent of theta is opposite, there's 3 again, over adjacent, 4. If we do the inverse tangent once again, and calculate that up, those two cancel. The inverse tangent of 3/4 is 36.869, yada, yada, yada. So we're talking about 36.9 degrees. So I'll mark this angle up here as well. And those will be useful when we start to work with individual joints during this problem. All right, it's finally time to calculate the internal forces. That means that we're going to be finding how much force each member in this truss is feeling. And to do that, we're going to focus in on one joint at a time so that it makes the problem much less overwhelming and easier to calculate. First, we're going to start off with joint A, because I know a lot about what's going on at joint A. I know what FAX and FAY are, and there's only two unknowns at joint A. That would be member AB and member AC. So what I'm going to do is draw a free body diagram at joint A. FBD for short. So here's an FBD at joint A. And I highly recommend labeling your work as you go through these problems, just because staying organized is one of the keys to success. So at joint A, here is A right there, that little dot. And I'm going to draw all the forces that are acting around joint A. I've got two external reaction forces, and you always draw these exactly as they look in your original free body diagram. So FAY is pointing up, FAX is pointing to the right, and then there are two members that are attached to joint A, AB and AC. Now I always draw my members pointing away from the joint. That means that I'm drawing them in tension. I try to stay consistent that way, so members, for me, always get drawn pointing away from the joint. And I'll label this one FAB and FAC. Okay, now when you're working on a free body diagram, there are two equilibrium equations you can use. Sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. No moments when you're doing internal forces. Let's go x direction. All right, in my little free body diagram here, only focusing at joint A, what do you see acting in the x direction? Well, I see FAX pointing to the right, so that's positive. I see FAC also pointing to the right, so that's positive. And you might be thinking, okay, well that's it. But don't forget about FAB over here. This force is acting partly in a horizontal direction. It's not completely horizontal, but part of it is. And so we need the horizontal component vector of FAB. And if you remember back, to get the horizontal component vector, you take the magnitude of the force, that's FAB, times the cosine of the angle that that force is acting at. And this is why we did the trig earlier. We already found that this right here is 31 degrees. So FAB cosine of 31 degrees. Those are our three horizontal components, and they total up to 0. Now that I've written this equation to begin with, you'll notice there's a lot of variables going on. You can substitute anything that you've already found. So for instance, I already found that FAX is 0. So I'm just going to cross that guy off since he's 0. Unfortunately, I don't know FAC or FAB yet, so I'm stuck. But no worries, that's why we've got the sum of the forces in the y direction. They total up to 0 as well. So let's look at what's going on in the y direction here. I've got FAY, which is pointing up, so it's positive. And I've got the vertical component of FAB. It's partially pointing upwards, so we need just the vertical part of it. Remember that that would be FAB. And you use sine for the vertical component. Sine of the angle, so it's just sine of 31. Similar to what we had up above, except we're using sine instead. Now those are the only two things acting vertically in this free body diagram. So this equation looks a lot simpler. Let's substitute in what we already know. That would be FAY. We found up above that FAY is 44.4. And now it's just a matter of doing a little algebra to solve for FAB, because that's our only remaining variable. Now it looks like I didn't give myself enough room here, so I'll try to sneak it in. We're going to subtract 44.4 from both sides. So we'll be left with FAB, sine of 31 equals negative 44.4. And now to finish solving this, FAB is being multiplied by sine of 31. We'll want to divide both sides by the sine of 31. So I'll sneak it in here. Divided by the sine of 31. I'll just cancel this guy out. Pretend like I squeezed it in there. Dividing by the sine of 31. Let's see what that equals. Negative 44.4 divided by the sine of 31. I come up with negative 86.2. So that tells me that FAB is negative 86.2 pounds of force. So there's one member complete. Now you can go back to our previous equation up here and substitute FAB into this equation, and we can solve for FAC. So negative 86.2 goes here. 86.2 times the cosine of 31. FAC minus 86.2 cosine of 31. So depending on how comfortable you are with working with equations left in trig form, I would say go ahead right now and let's see what this is as a decimal. So negative 86.2 times the cosine of 31 comes out to be negative 73.887. So let's talk negative 73.9. And you can see there's only one step left to go to get FAC by itself. Add 73.9 to both sides. So I end up with FAC equals positive 73.9 because I added it over here to the right. There we go. 2 members found already. That's everything you can do at joint A. There's nothing else you can do here. So it's time to move on to another joint. When you look at any of these joints up here, you're welcome to pick whatever you like. But it's helpful to move across the joint using the information you've already found and go on to a joint that you know a little bit more about. So I already know AB and AC. I'm going to say let's go to joint C. So let's go up here, up above, nice and high. Let's do a free body diagram at joint C. So here is C. And what's going on at C? Well, I've got 3 members there. No external forces at all down here, and no applied forces at all. Even though 100 is lined right up with C, you really want to focus in just on joint C, and there are only 3 members around it. So those are the only things that go in this diagram. I've got AC, CD, and then BC. Now all 3 of these are members, so I draw them going away from the joint. Let's see, this is FAC, FBC, and FCD. Okay, those 3 members right there are the only things that are acting around joint C. Now notice, even though I already know AC, I still wrote the variable form of it because it really helps to use the variables first, set up the equations, and then later on substitute in anything you found earlier. Okay, let's go forces in the x direction. What do you see in the x? Well, I see 2 members, AC and CD. AC is pointing to the left, so it's negative. And CD is pointing to the right, so it's positive. Those have to total up to 0. And you can see here that if I add FAC to both sides, I end up with FCD equals FAC. They're both positive. And now you can substitute in what we found earlier. FAC is 73.9, so FCD must be the same. And you can probably see why, and that's because AC and CD are end-to-end. They're members that are end-to-end, so they have to be feeling the same amount of force. Let's go ahead and do the vertical direction. That shouldn't take us too long. The sum of the forces in the y direction have to total to 0. And notice that FBC is the only thing in the y direction. Therefore, FBC is 0. There's nothing else around it to cancel it out or to make it have to total with anything, so FBC must be 0. So therefore, this middle member right here is actually not feeling any force right there. All right, we've exhausted everything you can do at joint C, so we've only got one member left to go. Remember, we have 5 members, and I've found 1, 2, 3, 4 of them. So one left to go. The only one I haven't found is BD. So let's go ahead and do a free body diagram at joint D. Okay, joint D has got the center of the joint right here. Actually, I'm going to draw the free body diagram over here on this side and do the calculations right here. In this diagram, I've got FDY pushing up. Now remember, this guy is an external force. That's why it gets to be drawn towards the joint. It's not a member. Members are the only ones that I draw always going away from the joint. I've got 2 members here, CD and BD. So here's FCD and here's FBD. Not to be confused with free body diagram. This is the force of member BD. All right, so in this picture, those are the only things that are acting at joint D. And remember that we found earlier that this is 36.9 degrees. Now I'm going to tell you one thing to watch out for is, remember from the past we talked about always measuring our angles from the positive x-axis. And notice that in this picture right here, if you think about the joint as the origin, the positive x-axis is right over here, this little dashed line. So how many degrees is it to go from the positive x-axis here to FBD? Well, let's see. A full turn all the way over here would be 180. So if we took 180, subtracted off 36.9, 180 minus 36.9 comes out to be 143.1 degrees. That's the value that we're going to use in this calculation. Okay. It doesn't really matter which one you want to pick, if you want to do the forces in the x direction or the forces in the y. Let's just pick one and see if it works. I'll start with forces in the x. All right, what do you see acting in the x direction? I see FCD pointing to the left, so that would be negative FCD. And I see the horizontal component of FBD. So not the full thing of FBD, just the horizontal part. That's why we're going to write it as FBD cosine of 143.1. And some people have asked me before, hey, how do I know if I should put a plus or a minus in front of the angled term, the one where we use cosine or sine? And this is where the nice thing about measuring from the positive x-axis comes in. If you always measure your angles from the positive x-axis, always just stick plus in front of your horizontal or vertical component, and then the cosine or sine will handle whether it should be positive or negative. So what I'm saying here is always put plus in front if you're going to use cosine or sine, as long as you're measuring from the positive x-axis. So those are our only 2 horizontal vectors. They total up to 0. Let's fill in what we know. I know FCD from last time. FCD is right up here, 73.9. There's a negative 73.9 because there's a negative sign right here. Plus FBD, cosine of 143.1. To solve this, let's add 73.9 to both sides. So that would cancel this away and put the positive 73.9 over there. .9 is now over on the right, it's positive. One last step, divide both sides by the cosine of 140, oops, the cosine, don't forget that. Cosine of 143.1 degrees. Okay. Okay, these two should cancel each other away. And now I need to figure out what 73.9 divided by the cosine of 143.1 comes out to. It looks like FBD equals negative 92.4 pounds of force. All right. That is all 5 members. But there is one thing left to do. Here's the last step to finish this problem. You may have noticed that a couple of our members ended up with negative values in their calculations. FAB and FBD both ended up with negatives on them. When you're doing calculations on internal forces, remember that we drew all members pointing away from the joints. We drew them in tension. And yet if we get negatives, then that means that these members are not in tension, they are in compression. So what you need to do to finish this problem is tell which members up here are in compression and which are in tension. Positive values, since we drew every member pointing away from the joint, positive stands for tension. So put a T after it. These two are in tension. And then the two values that ended up negative mean compression. So rather than calling them negative in our final list of solutions here, rather than putting negative signs in front, you, behind them, say that they are in compression. And of course, since the FBC is not feeling any forces, you don't need tension or compression on that. That concludes our lesson on how to solve a truss. I hope these videos have been helpful to you. And if you have any questions, please don't hesitate to leave comments below or write to me on my email. Thank you very much.